Hi class, we're on the next section, chapter 2.5, Solutions by Substitution. Now last time I taught this section, this was probably the least favorable section for students to have to deal with. It's quite a long video, I'm assuming, because the write-up and the amount of coding I had to do for this was quite long. However, this is an approach that would be fairly common, right? So basically, we're going to use this approach whenever our previous methods fail, right? So if we can't separate the variables, if we can't put it into a linear form, for linear equations, where we can do the integrating factor, or if it's not an exact solution or an exact equation, then we probably have to do some sort of substitution, right? So a substitution will basically, just like in algebra, it'll take us from a difficult form and help us to get into a form that we are comfortable with, right? And then once we're in a comfortable form, we solve with the method that we know, right? So our goal is basically to make a substitution so that our equation is now separable, or that it is now in the linear form, or that it is now in an exact form, and then we can apply the previous three methods that we learned, right? So that's our goal, is to try to pick out the right substitution. And of course, this is all by trial, right? So we'll try to do separation. We'll try to do the integrating factor. We'll try to see if we can use an exact form, right? And then find an integrating factor for the exact form. Maybe that doesn't work either. And then we have to say, okay, now are there some substitutions that I can make, right? And again, when we're looking for substitutions, we're looking for sort of some key ideas, right? We're looking to see if it's in a form that we recognize, oh, I've seen this before. This means that I need to make this kind of substitution, or I need to make this kind of substitution. So again, chapter 2 is really on pattern recognition, right? So you can try a couple of forms, a couple of methods out. If they don't work, then you kind of just go down the line. If that's not working, then maybe, well, ideally you've done enough of these that you're like, oh, I'm familiar with this pattern, right? I know exactly what to do here because this is familiar to me, right? So that's kind of the hopes and the dreams here. So without further ado, let's go ahead and go through this lecture. Now, you know that when I kind of talk and ramble at the beginning, I repeat a lot of what's going to happen on the first couple of slides. So I'll kind of, we'll read through them, but we'll see what happens, right? So again, just repeat. There will be times when a substitution will turn a difficult first order DE into a form that we're more comfortable with, right? So if our equation is in the form of an exact equation, for instance, we try to use the substitution y equals u of x, or x equals v times y. The substitution that we make is really based upon the equation itself, okay? And so if we have an exact form and we make this substitution, we'll be able to turn it into a separable equation, right? Which is nice because separation of variables is a fairly easy method. Although I think that this exact form was also easy. So like I said before, when it comes to exact forms, we have a test to see if it's exact. If that test fails, then most of the time, a lot of times, I guess, we can find an integrating factor that will make it exact. But if that fails, then we can make a substitution. We should be able to make a substitution, I should say, that will turn it into a separable equation, right? So when we have exact equations, it's nice, although it's also not nice because we have 3 attempts that we have to make, right? We have to check to see if it's separable. I'm sorry, to see if it's exact. If it's not exact, we can look at an integrating factor. If we're not able to find an integrating factor, then we try to make a substitution, right? So for these ones, there's kind of a 3-part, a 3-tier approach that we go through, okay? So depending on the form of our equation, as I said before, is going to determine which form of the substitution we want to make, right? So if my m function and n function both have a variable of x present, then it's going to be beneficial to use y equals u times x, okay? We then differentiate implicitly using the product rule, right? So here we're doing the derivative here. So again, remember y is a function of x, and so is u. So we'll use the product rule here. So dy will then be the product rule on the u times x, right? We're assuming u is a function of x as well. Okay. So we then substitute for y and dy, this and this, into my equation. And then we should have nothing but x's, right? If this is an equation, all my y's will now turn to something with x. My dy now has nothing but x's in it. There will be no more y's in my equation, only x's. And then we can separate my equation out, right? Now, if both of these have y's present, then we'll use this substitution instead, so that my equation has nothing but y's in it, right? And we'll do the same sort of differentiation implicitly. Okay, so all of my x's will turn into something that have y's there, right? So if there are y's present in both, I'll make a substitution so that there's only y's. If there are x's in both, I'll make a substitution so that there are only x's, right? So that's kind of the goal. Now we're going to run into cases where there's x's and y's in both. And then you're like, well, what am I supposed to do? It's up to you. You choose whatever you want, to be honest, right? Whatever you're more comfortable with. A lot of times, maybe both equations have x's, but you want to substitute for y's anyways. That's fine. So here the substitutions are kind of arbitrary. There are times where you will get stuck. So this is really just guidelines for trying to make it as easy as possible. But you can really go for either one of these in kind of any case, right? It's really up to you. But these are when it's the best time to use whichever one. Okay. It is also a good idea, I guess we could say, right, to use the x version, x equals v times y, whenever we have an m function that is simpler than the n function, right? So you kind of have a three-tier sort of way. You can kind of go with this advice always, or you can kind of say, okay, well, let me go through these two as my piece of advice. It's really up to you, but these are like these are the guidelines for when you should use one substitution over another. They're not hard, fast rules. They're just there to kind of help you through the process. Okay. And again, right, if one substitution doesn't work, then just try the other one. So again, maybe you make one substitution and you get stuck. Go back to the beginning and use the other form, right? So if y equals u times x doesn't work, go back and substitute for x instead. Okay. So let's go ahead and do an example. So let's solve this dE with this initial condition such that x is always strictly positive. Okay. So here we have xy times dy dx plus 4x squared plus y squared equals 0. So it doesn't look like it's an exact equation. However, again, remember, it won't always look that way. Sometimes you have to manipulate it first. So let's get it in the dy dx form, right? So let's separate the dy and dx. So we'll multiply everything times dx. This is not separable, right? So we can't write it as a separable equation, which is very clear here because if we multiply times dx, I have x and y in a dy, and then 4x squared plus y squared times dx. So the x's and y's are mixed up with the dy and dx. There's no way for me to separate those, okay? You can do a little bit extra work on the side to verify, but you won't be able to separate it. You also won't be able to put it into a linear form, okay? Mostly because there's a nonlinear term here, right? So it's very clear that it is not a linear equation. Also, with the y times dy dx, if I divided everything by y, I would have x times y prime. This would turn into a y, but I would have 4x squared times 1 over y, which is also a nonlinear term, right? So I can't write it in this form where it's y prime plus px times y equals some function in x. Okay. Again, there's a nonlinear term of y squared, or even if I divide by y, I'd have a nonlinear term of 1 over y, right? And I would not have a qx term. I would not have a function that is only in x somewhere. So I take my equation, I multiply it by dx as I said before, right? So that'll clear it here, and then here both of these terms are multiplied by dx. So you could do it one at a time if you want, and then factor it out, or just recognize that this is the dy term and the dx term. So that means that this is my m and this is my n function, right? When I put it in the correct form, whatever was attached to the differential in x is your m function. Attached to your dy was your n function, right? So, oops. So I have this here. Okay, if I differentiate this in terms of y, I get 2y. This is held constant, so it just goes away. If I differentiate this in terms of x, the y is held constant, and the x actually goes away here, and I get just y. These things are not equal, so it is not exact. Okay. Now, from here, I could use an integrating factor. Okay. You could check on your own and actually create the integrating factor, and notice that when you get one of these, right, the my minus the nx, I get y. And when I put that over n, the y's cancel. It's only in x. I have an integrating factor at that point. I can solve this using an integrating factor. However, that's not the point here. The point here is to solve this by substitution, right? So that you're familiar with the substitutions. So if you want to, you can go ahead and pause this video and solve this by integrating factor and see and check, I should say, that your solution matches up with the solution we're going to derive now, right? So if you want to, go ahead, pause the video, and solve this equation using the integrating factor, okay? And then that way you can go ahead and write with us the notes that we're going to have for a substitution, right? So go ahead and pause now if you want. Okay, so welcome back. So to finish this out, if we were to make the integrating factor, it would be basically just x, right? So this turns to e natural log of x, which is just x. So you can turn this into an exact equation rather easily, right? So again, like I said, that's not the focus of what we're doing right now. So there may be times where it's easier to do an exact equation, or maybe substitution may be simpler, so it's nice to have multiple methods. And also, as I said before, maybe you can't use an integrating factor and you have to use a substitution. Okay, so here note that in my mxy and my nxy, x and y are present in both, right? So it doesn't really matter which substitution I use, because it's not that m has an equation in x and n has an equation in x. They both have x's and y's present, right? So I can choose either y equals ux or x equals vy. It doesn't really matter. However, it also said that we said that a lot of times this is easier to use if m is simpler. I don't know that m is necessarily simpler. I think x times y is very simple, right? So simple is actually kind of it's up to the reader at that point, or the mathematician who's working on it, to say, oh, this is simpler than that. So here we're just going to go ahead and use the substitution y equals u times x. That's pretty standard, so that's the one that I'm going to go with, right? So I know that y equals u times x, and the derivative gives me the product rule of this form, which I gave you already. Okay, so when I plug this into my equation, right? So let's go back to my equation for all of us here. Y is ux, so this turns to x times ux, right? And then I substitute my dy. Here, y is squared, so I'll get ux squared, or u squared x squared, right? So that's what's going to happen here. I got u squared x squared. I'm going to get x times y times dy. So here's that substitution that I had, right? So when I start to combine things together, right, I'm going to have u squared x squared dx. Okay, here I'm going to get an x squared u squared dx, right? And here I'll get a u x cubed du, right? And then here I'm really taking that first term that I had with the dx and this 4x squared with the dx, and I'm just kind of pulling out that common dx term. Now you might be saying, well, why'd you pull out a common dx here but not with the common dx here? Or how come you didn't take this u squared x squared and add it to be 2 u squared x squared? I just didn't. Okay, there's no rhyme or reason. It's just how it ended up being when I started to do this work myself. Okay, so really what I'm trying to do is I'm just trying to separate everything. I'm trying to separate the X stuff and the U stuff, right? Because we said for these exact forms or almost exact forms, making this substitution should turn it into something that's separable. So my goal is really just to separate everything out. So I'm really just trying to pull out this X term and trying to get this U's isolated in this side. Here I have the U's and X's, so I would like to separate my U's and X's. Right, and let's look at this form just a little bit too, right? Why would it be advantageous just a little bit? Well, I have equals 0 on one side, okay? And notice I have U and X, U's and X. I have a common term here of X squared, right? X squared times this stuff, X cubed, there's at least an X squared in here and an X squared here. If I divide everything here by X squared, the X squareds really just go away because I have 0 on the other side. So that's pretty nice because now I have U's, and U's. So now the goal is really to try to get the dx stuff together, okay, and the du stuff together. So what I can do is I can factor out the dx. So if I factor out dx, I'm going to have 4 and u squared and u squared. So there's 2 of them here. So I just did it a little bit later than maybe you would have at the beginning, which is fine. It still happened, right? And then I have ux du. That's kind of staying the same. So now I want to really try to isolate the x's and the u's. Now that I got it simplified down to a single du and a single dx term, I would like to try to get these u's over here with the u and this single x over here with the x. So I probably need to get everything onto a separate side of the equation first. So let's subtract one of these. Okay, I don't know which one. I guess I subtracted this one first. So then now I can start to divide stuff, right? Now I can, in order to get x is over here, I can divide by x. In order to get all the u's over here, I can divide by these u's, right? So I got 1 over x dx, negative u divided by 4 plus 2u squared du. And then now all that's left is to integrate both sides, right? I separated my variables. This is just natural log of x. Here I can pull out a 2 in the denominator, right? There's a common factor of 2 here. So just negative 1/2, pulling out that constant of negative 1 as well. And so we've seen several times me do I want to say u sub, but I already have u, so we can call it a v sub or a w sub or some other variable. But it's basically a u sub for this denominator here, right? So I'll say w is 2 plus u squared. So dw is 2u du. Okay, and then I have that 2u du, so I can move it over because I need to substitute u du. So that's 1/2 dw. So I'm really just going to multiply this by another 1/2. So it'll be negative 1/4 by the integral of 1 over w squared dw, right? Oh, I'm sorry, this is a u squared, so just a 1 over w. Alright, so my natural log of x is this integral here. This is just natural log of w, right, plus c. Here I don't need the absolute value sign because part of my condition was that x is strictly positive, right? So I don't need an absolute value sign here. I do need to go from the world of w's back into the world of u, okay? And then from the world of u back into the world of x's, or y's, I'm sorry, right? Or x's. Or I should say the world of y's and x's, right? So in order to make the substitution, I need to take this sub that I made, which is y equals ux, and solve for u, right? So it's very straightforward. U is y over x, right? So I need to make that substitution into here. So natural log of x is negative 1/4, natural log, absolute value, y over x squared, plus 2, and absolute value plus my constant of integration. So we can't solve for y explicitly here. So we would solve for it implicitly, right? Because I have a y squared term. So I don't want y equals plus or minus square root of some stuff that's still 2 different functions, right? So we just really want to try to solve for y squared. So we're going to have to basically raise everything to the power of e to be able to access this y, right? It's inside of a function, so I got to get it outside of this function it's inside of. So undoing natural log is by raising everything to the power of e, right? So that'll give me this crazy thing, right? I'm just really showing you this so that you can see what I'm doing. So that's going to give me just x here, and then I'm going to have all of this raised to the power of e, right? So this e to the plus c just turns into a constant. I'm going to write it as e to the c, however, but it's really just going to turn into another constant. So this is going to be x equals some constant, which we'll call c, and then this thing to the negative 1/4 power. So again, if I were to try to solve for c here using my initial condition, then what's going to happen is as I go through the process of isolating y, I'm going to keep doing more and more and more math on this, right? For instance, I'm going to need to take the negative 4th power here in order to cancel out this negative 4th root, and I would have to do that to both sides, right? So it's easier just to keep it as is and just keep rewriting it as a constant c, and then whatever I get at the end, that's what I should have gotten if I were to try to find c here, or I guess here in this case, right? And then done all of these operations in arithmetic. So it's always easier just to kind of save it for the end, as I've been saying. Okay, so this is just a constant, and then here I can actually write it as a square because my goal is to solve for y squared, right? So I want to get all this stuff out of the way, so it's better to just kind of have it in this form so I can keep my eye on the prize and say, boom, that's what I'm trying to solve for. So like I said before, I'm going to raise everything here to the negative 4th power. So I'm going to raise this to the 4th power as well. So I'll get x to the 4th is some constant that I got way at the beginning to the 4th, which is just another constant, right? I don't have to do the math on or the arithmetic on this thing. I just keep writing it as c, right? So this will be c x to the 4th minus 2 is y squared x squared, right? So I did quite a little bit of math here, arithmetic. Okay, I basically raise everything here to the negative 4th power, and then I divide, so I'll have x 4th equals c times this stuff. I divide by whatever that constant is. That's still just a constant, so I can call it c times x to the negative 4th, and then subtract 2, and I'm left with this, right? So that's why we have this here. Never doing the math on the constant till the very, very end. And then I want to solve for y squared, so I just multiply everything by x squared, right? So this is negative 2x squared, and then this will be c times x to the negative 2, right? And there we go. That's my implicit solution. Y squared is cx negative 2, negative 2x squared. Or if I wanted to write it as a single function, right? Because this is c over x squared minus 2x squared. So the common denominator then is x squared. So I multiply this top and bottom by x squared, which turns that to an x4. Right? So I can write it like this. If I don't like negative exponents, I can combine it into a single rational expression. And then now I would use my initial conditions to solve for c. Right? So here, y squared is 49. Plug in 2 for x to the 4th is 16. Solve for my c, and you should get 228. Now, if you had done this substitution here at this point to try to get a c, you would have got something completely different. And then as you did the arithmetic on it, you should get the same thing. But again, it's a lot more work. Try to save the arithmetic for the end if you can, right? So therefore, my final solution implicitly is y squared equals 228 minus 2x to the 4th all over x squared, okay? Now, if we put it in exact solution form, remember exact solution form is some function equals a constant. I need to move all of this stuff over to the other side equal my constant value. And so you should get something like this. So if you solved it using that integrating factor at the very beginning, as I told you before, to kind of do on your own, this should be the solution that you got, or maybe 2x to the fourth times x squared y squared is 228. That would have been okay as well, right? But ideally you have some function equals a constant in your exact solution form, right? So there we go. Okay. So next, Bernoulli equations. Okay, so our next form that we're going to look at is Bernoulli equations. So for Bernoulli equations, our goal is to turn it into a linear form where we can use an integrating factor. Okay, so these typically have a form that are almost in linear form already, right? Whereas that g of x function now has some power of y attached to it, right? So it's not so much that it's like a sign of y in here, but there's y to a power attached to a function of x, right? So if we have a function that looks like this, we can make a substitution to turn it into a linear equation where we can now have I of x is e to some power, right? So our substitution will make our equation into a linear form where we can use an integrating factor on, as I said, right? So our steps are take that highest power of y that we have and divide the entire equation by it, okay? Then we're going to make the substitution u equals y to the nth power, where y to the m, or m I should say, is the new largest exponent of y, right? So we divided by our old highest power of y. We're going to make a substitution where u is now our new largest exponent of y, okay? Then we're going to differentiate this function implicitly, right? So we're going to get du is m dy ym basically, right? So ym minus 1, I should say, times y prime. So we're going to treat this as a power of m, so m comes down, this reduces by 1, and then you have y prime. So basically the chain rule on this power of y. And then we substitute for u equals ym and y prime. Now, there's a little bit to be said here. We're not substituting in u prime necessarily. We're actually going to substitute in y prime. So we'll solve for y prime, possibly not even y prime. Probably it's possible we take m minus 1 y prime, and we substitute that. So we may have u prime divided by m, and then this is the substitution we'll have. It really depends on what your equation looks like, okay? But regardless, once we substitute, our end goal is to have no more y's and have a bunch of u's everywhere, basically, okay? So once we have all the u's everywhere, we're going to solve the linear equation with the appropriate integrating factor I times x, okay? Okay, so let's do an example. So let's solve y prime plus 4 over x times y equals x cubed times y squared, right? Here we have the initial condition, y of 1 equals -1, x is strictly positive. So it's very clear here that our largest power of y is here, y squared, so we'll have u equals y squared as our substitution. Here we know it's not separable because it's pretty much in the form of the linear form that we need. Not only that, but if we did try to write this as dy dx and then we multiply dx everywhere, there's pretty much no way that we're going to separate these things. It's also not linear because we have a non-linear term. So it's in the form that we want, right? There's a non-linear term, and it's also not an exact equation because even if we did separate them out, it would look like this, right? So again, if I wrote this as dy dx and I multiplied everything by dx, it would look like this, and there's no way that this is the same first partial as the same function that this is a first partial of in terms of x, right? So we need to try a substitution. Okay. So the equation is a Bernoulli equation, so we divide by y to the n, right? So here y to the n is going to be that y squared. So when I substitute that in, right, everything's going to go down, right? So I'm dividing by y squared, so it's the same thing as multiplying by y to the -2, right? So y to the -2, this is going to go down by 1, and then this is going to disappear, right? So now my new highest power of y is y to the -1, right? So that is what I'm going to set u equal to, right? U is equal to y to negative 1. So when I differentiate this now, du will be negative y to the negative 2 times y prime. Okay. So again, notice here that I have literally this exact term. Y negative 2, this is y prime is just written as dy dx, right? But this term is here, except it's the opposite sign. So in order to get them to match up, right, this needs to become negative u. So this whole thing is negative u, right? So if I write this in the du dx form, right, which is in the dy dx form, which is what I did here, instead of the prime form, that's what I get. So when I move the negative over, right, this becomes a positive. So this will be negative du dx. This will be 4 over x times u, because y negative 1 is u. And now it'll be in a linear form, right? I got my y prime, I got my u. I am multiplying everything times a function of x. At the end, I have a function of x. Okay. Now, ideally here, I'll change the signs, everything, because remember your p of x function is when this is monic, meaning the coefficient is just a positive 1. So this is my p of x now, and this is my q of x. So my integrating factor is going to be e to the power of the integral of negative 4 over x, which is super nice and easy to solve for. So I just have x to the negative 4 as my integrating factor. Okay, so I take my integrating factor and so again, this is what I'm solving. I'm not coming all the way back up here, right? I'm solving this. So I'm going to multiply x to the negative 4 times this equation. Okay, and remember, once my integrating factor comes into play, this is now the product rule, right? So I take this as one of my functions, and then I take the u as the other function in the product rule. So that's x to the negative 4 times u inside the derivative, right? Remember, it's very, very formulaic at this point. Okay, so and if you're not sure if that's what the ones you should have chose, we'll just differentiate this and you will get this left side out. Okay, so now I integrate both sides with respect to x, right? So that's really just going to get this thing to cancel, and then this is going to this is 1 over x at this point, right? So this will turn into negative natural log of x, and then this will add an integrating factor, right? And so now, ideally, normally we would solve for y, right? But the problem here is that I don't have y, I have u, right? So I can make my substitution back that I made. Where did I? Here we go. U equals y negative 1, and then I can solve for y, right? So here I can solve for u first, or I can solve for y first. It really doesn't matter in this case. I'm just following the standard procedure. So I decided to multiply everything by x to the 4th instead of plugging in y and then solving. It's all the same thing, right? So here I multiply everything by x to the 4th. Then I make my substitution, and then I can solve, right? So since this is 1 over y, it would be the same thing as me multiplying this times y and then dividing by this, right? So here, it's really just me kind of flipping the reciprocal here, and that's my solution. Except that I have this constant, right? So I can pull out the common x to the 4th if I wanted to. There's all kinds of things I can do here. But really, I just need to solve for my constant of use my initial conditions to solve for my constant of integration. So when I plug everything in, output is negative 1. Here, when I plug in 1, this whole thing goes to 0. I get c times 1. So negative 1 is 1 over c. Very nice when I plug this in, right? That's going to give me c is negative 1, right? Multiply times c, move the constant, the negative 1 back over. Very straightforward. C is negative 1. So my final answer I can write as the following, right? So you might say, well, why is this positive? Well, because it's negative here and negative here. So I factored it out. And it's much clearer to write it as to the power of negative 1 than 1 over this thing. It's the same. You guys are smart. You can figure it out, right? So that's my solution at that point, and I was able to find an explicit function because I solved for y directly, right? Now, the last substitution we're going to go over is an easy one to spot when you see it, okay? It's basically when we have y prime or dy dx on one side, and on the other side it's very, very clear that we have a composition of functions, okay? So if we have a composition of functions, then we can make the substitution that u is the inside function, and then u prime is just the derivative of that inside function, right? So we're just really looking for the substitution of the inside function in the composition, because then we'll now have a function f in terms of u. It makes it a lot easier to do that, and we'll be able to separate our equation at that point. Okay, so let's go ahead and do an example. Here I have y prime minus 4x minus y plus 1 squared equals 0. Y prime, or I'm sorry, y0 equals 2. So it's very clear here to see what my function is. Okay, so that's going to be my u, right? So I move everything over so that it's in the correct form. I make that substitution. U is 4x minus y plus 1. And then I'm going to find the derivative of u. So here, remember, u is a function of x, right? Y is also a function of x. So I'm going to differentiate this with respect to x, which means that y will go then into its prime notation. If it was like a y squared or something, then I would use implicit differentiation on it. So u prime equals 4 minus y prime. This 1 goes away. Here this x goes away, and then y turns into y prime, right? dy dx. This is du dx. So solving for y prime gives me 4 minus u prime. Okay, so then that's the substitution that I'm going to make. So then I'll have u's everywhere because instead of y's, right? So same thing. So this will be 4 minus u prime, and I'll have u squared here, right? So for 4 minus u prime equals u squared. Move the 4 over, okay? Change the signs, and then this is what we have. So now it'll be very easy to try to separate these. I really just got to bring the u squared over here. Write this as du dx, and then move the dx to the other side, right? Not a huge problem at all, right? So then this is what we have. Okay, du dx. I divide this on both sides, multiply the dx. So this will just turn into x, and this side will separate since it's a perfect square, right? So integrating this gives me x plus c, right? The constant of integration. Here, this is going to take a little bit more work, right? So when we have something like this, we need to use partial differentiation, right? And that's because this is a perfect square, or I'm sorry, difference of squares, right? Using a u sub here is not gonna really work. You can try a u sub, but it's not gonna be beneficial, right? Because I don't have a u up top. When I differentiate this to the 2u du, there's no extra u here, so the u sub's not gonna work too well. We can decompose this though into two rational functions, which will be easier to differentiate. So we will do partial fractions here, decomposition of partial fractions, which if you've done linear algebra will be a super easy breeze. If not, we'll go through it the long way. It's not really that much longer, but here I know that this is going to be equal to the form a over one of the factors plus b over the other factors. Now if I had different factors here, your partial fraction takes different forms, so just make sure you brush up on your partial fraction decomposition, okay? But this is a pretty straightforward standard problem. We don't have to worry about, you know, the ax plus b over the quadratic factor or anything like that. Here is an easy one, okay? There's no repeated factors either, so that's nice as well. So here we're basically going to clear the denominators. We'll multiply both sides times 2 minus u 2 minus u times 2 plus u. So here I'll have just 1. Here I'll have a times 2 plus u, and here I'll have b times 2 minus u, because things will cancel out, right? So now I need to multiply these out. So 2a plus ua plus 2b minus ub, right? And then now I can just equate the two sides, right? This is a constant. This is a constant. My variable is u. So that means 2a plus 2b is -1, right? So the constants have to be equal. Here the variable parts have to be equal. There's no u's on the other side, so AU minus BU has to be 0. But I also don't need the u, so I can just say A minus B is 0, and 2A plus 2B is -1. So those are my two equations that I get from equating the two things. So this first equation gives me A equals B. Then I can substitute that into here, right? 2B is just the same as 2A. So I have 4A is -1. Therefore, I have A equals B, which is equal to -4, right? A equals B here. Here, A is -4, so they're both -1/4. Plugging that back into my differential equation here, right? Sorry, not my differential equation. Well, yeah, my differential equation. This side turns into this partial fraction decomposition, so it turns into the integral of -1/4 over 2 minus u plus -1/4 over 2 plus u. I obviously took some liberties here and separate them because it's an addition of rational functions at this point, so I'll just write it as two separate integrals. Oops. Okay, two separate integrals, and I'll pull out that constant instead of keeping it on top and then having to pull it out later, right? So -1/4 times my one side minus 1/4 times the other one, right? So that's my partial fraction decomposition equals the right hand side. So now I need to do these two integrals, right? Pretty straightforward. I can use a u sub for both of these, right? So the sub is pretty straightforward. W is 2 minus u. So when I differentiate that, I'll end up with basically just 1 over w here. Okay. I can change sides. I changed it around a little bit. So when I do my integral, it's a very, very easy integral to get because the substitution is very easy. I need to substitute my u's, right? So if we come all the way back over here, what I had for u was this thing, right? I had u was 4x minus y plus 1. So I need to substitute those back into my equation. However, before we do that, notice that we have a common term on the outside. We also have a subtraction here between natural logs. So let's kind of whittle this down a little bit first before we get too crazy. We can make a sub here right now, but I think it'll be easier to work with this as is before we throw in a larger equation, right? This larger thing in there. So subtraction means that you divide, right? Especially since we have a common exponent, if you will. So I can write this as 1/4 natural log u minus 2 over u plus 2, right? Which is nice and compact, right? And then if I want to get rid of the natural logs, I can raise everything to e, which I would have to do anyways. So it's better to do it here than when things are crazy, right? So this is e to the x. E to the c is just a constant, right? So this is from the rules of exponents. Here, the natural log cancels. I still have this inside, but I'm raised to the power of 1/4 when I raise this to the power of e. So that's looking a little bit easier to deal with than what I wanted to do at the beginning. So I can still try to isolate this. Remember, I'm trying to get the u's to come out because when I make my sub, that's where my y's live. So here I can multiply everything times the 4th power. So again, c to the 4th is just another constant, so I don't have to keep track of the math here yet. Okay, and so now that I've isolated, I simplified it a little bit, now we can substitute our u back in. And then my constant of 2 here is going to interact with what I have, which will be pretty nice, right? This will give me a -1. This one will give me a 3. Then I can multiply both sides by this denominator, which will give me what you see here, right? 4x minus y minus 1 on top. And then c times e to the 4x times each term here on the bottom, right? So why did I do that? Well, I want to isolate my y's. So if I just kept c e to the 4x as a common factor on the outside, I'm not going to be able to get to my y's until I distribute that in anyways, right? So I'm just kind of skipping a couple of algebraic steps here because this is diffie q. You should be able to follow quite well. I'm going to get all the y terms on one side, all the everything else on the other side, right? So I'm going to add this over. I got negative y, and I just subtract 4x and add 1. Okay. Here I'm going to pull out the common y term, and then I'm going to divide everything by this factor that I have, right? Therefore, my explicit form of y is the following. I don't have anything that I can do left over here. There's no common factors. I can factor out e to the 4x and this c a little bit, but that's not really going to help me. I can't put it in a factorable form, so there's no point, okay? But what I can do is I can finish solving for c, okay? I have y of 0 is 2, so when I plug in 0 for x, 0, this goes to 3c, this is 0 and 1, so I get 3c plus 1. This turns into c minus 1, and then output of 2, right? 3c plus 1, c minus 1, 2. It's way easier to throw it in now because everything disappears. And then obviously I got to solve for c, right? So I multiply both sides by c, okay? Same thing I did before. I need to get all the c's on one side, so it would be easier to move this c over and move this 1 over. Oops. Okay, c ends up being negative 3. So when I plug it in, this will be my final answer. Okay, there we go. Those are our 3 examples for substitution. Okay, 2 of them turn into several equations. 1 of them turns into a linear equation with an integrating factor. There is the composition substitution, the Bernoulli substitution, and our substitution for almost exact forms.